Hello, this is the part two of our economic growth notes that we started, obviously, in the last set of notes. In that last set of notes, we talked about some basics in terms of definitions and sources of economic growth, as well as the role for public policy. What we're going to be doing in this set of notes is much more mathy and therefore analytical. What I want to try to suggest to you right now, and I'll come back to this at the very end of the notes, is that this is largely for illustrative purposes. I'm not going to ask you to be doing complicated math, but I felt that when I was reading through some of the stuff in the book that it wasn't as clearly explained as I would have otherwise liked, and so this is my attempt to try to remedy that. So, in the last set of notes, we talked about the idea that if we want to think about, well, we want to think about growth because we're talking about ideally improvements in our well being. And we are proxying that by increases in real GDP per capita, which is how we are defining our standard of living. And we noticed that, and again, our focus here is on the long run, so we're talking about potential gross domestic product. We noticed in the last class that if we disaggregate or split apart GDP per capita into these two components, there's a limit to how much labor and population growth can contribute to improvements in our standards of living. So because this L over population has an upper limit of 1, we are going to focus on increasing GDP per worker, which is both income per worker as well as output per worker. And this is labor productivity. So we focus on that as the means to increasing GDP per capita. And so our question for today is, what are the things that will increase output per worker, labor productivity, and what more can we say about them? So to get at that, what we do is we identify the economy's production function. So aggregate production function, this is the economy's production function. And what we're saying is that real GDP, so this is again, real GDP, we think of it as potential gross domestic product, is a function of things that are useful for producing output. So this A parameter is what we're going to use as our indicator of technological progress. And then we have these other inputs to the production process. And what we're going to do is develop a framework where we focus just on physical capital and labor, and for the moment abstract from or ignore, you could view it as holding it fixed, human capital, just to cut down on the amount of excuse me, notation. And the F here just means that we have some mathematical way of expressing this relationship. So here we go. Here it is. An aggregate production function that we use a lot in economics is what's known as a Cobb-Douglas production function. And a Cobb-Douglas production function is one that has a couple of nifty features to it. One of them is if we have these exponents that sum to 1, Then we have what's known as constant returns to scale. And constant returns to scale means that when we double these inputs, we're going to exactly double output. So in contrast, we could think about increasing returns to scale or decreasing returns to scale. But constant returns to scale means that if we double the inputs, then we exactly double output. Increasing returns to scale would be if we double the inputs, all the inputs, we more than double output. Decreasing returns to scale would be if we double the inputs, we less than double output. For the macroeconomy as a whole, constant returns to scale is a pretty good description of the way the macroeconomy works. And just to see that how this works, again, remember that we have this production function that looks like this. Let's think about what would happen if we doubled the capital and labor inputs. So we have 2k raised to the alpha and 2l's raised to the 1 minus alpha. What we can do is we can factor out the 2's. So we would have 2 to the alpha times 2 to the 1 minus alpha times a times k to the alpha and L to the 1 minus alpha. And so what that gives us is 2 alpha plus 1 minus alpha, and then a k to the alpha, L to the 1 minus alpha. And this sums to 1, so this is 2 times a k to the alpha, L to the 1 minus alpha, and this is y. So we have this is equal to 2y's. So this production function, where it is the case that the exponents sum to 1, gives us this condition of constant returns to scale. And as I said, that's not a bad way of thinking about the US macroeconomy. The other thing that you will see in an upper level econ class is that you can offer some interpretation to these exponents specifically, and it's not something that I need you to know for this class, but this is the share of income that is accruing to physical capital, and the share of domestic income that is accruing to labor is 70%. So 30% goes to capital, 70% goes to labor. If we included human capital in here, we would have smaller numbers for these exponents, but again, exponents that sum to 1. So that's a side note for right now. What I want to do, though, is to remind you that our focus here is on labor productivity and the things that we can do, or the way in which labor productivity is affected by the inputs. And so in order to do that, what I want to do is divide the left and the right hand side of the equation by L, so in moving from the first characterization of the production function to the second, it's exactly the same because all I'm doing is dividing both sides of the equation by L. But notice that what happens with this characterization, this is L to the 1, and so this becomes, right, a k to the alpha, and then L, the exponent would be 1 minus alpha minus 1. So that would be a k to the alpha, L to the negative alpha. And negative alpha just means we put it in the denominator over here. So that's how we get this relationship. And so what we can see is that output per worker, labor productivity, income per worker, is going to be related to this parameter of technological progress and capital per worker. And we'll add in here, just by way of conversation, the relationship to human capital per worker. But this is saying that output per worker, which is what we want to think about because that correlates with output per capita, and our notion of standard of living and well-being is related to technological progress and capital per worker, physical capital per worker. And this is just what we said in the prior set of notes, but now we're just doing it with a bunch of letters. So the other thing that is true about a production function that looks like the one that we've characterized is that there are diminishing marginal returns. And so sometimes students get confused between returns to scale and diminishing marginal returns. So returns to scale is asking about if you double all the inputs, what happens to output? And we've said constant returns to scale is our model for now, so it doubles. Diminishing marginal returns, we've talked about in a couple of instances in this class, but in this context, what we're doing is we're saying, what if we vary one input and hold all the others fixed? What can we say about output? Okay, so what we are what we have as a empirical proposition, and one that we've talked about, as I said, at a couple of other spots in the semester, is the idea of diminishing marginal returns. That's in a generic sense. It says if we do or have more of something, the extra contribution to our satisfaction is going to be smaller. So in this context, as we have more and more and more of one particular input in the production process, it increases output, but by a smaller and smaller amount. So how do we look at that? Well, we're now, though, we need to remember that what we have in our characterization of the production function is capital per worker, and what we're measuring as well is not just output, but output per worker. And so to illustrate the idea of diminishing marginal returns, what we're saying is we can describe the production function. Again, what we said, this production function is y over L is equal to A times K over L to the alpha. That's our characterization of the production function. And what we can observe is that if we have a given change in the quantity of physical capital, and correctly per worker, so this size and this size are exactly the same. Initially, when we have very little capital per worker, it causes a large increase in GDP per worker. When we have more capital per worker, then the extra contribution to output per worker is smaller. And we've talked about this again earlier. We could think about, adding a machine to the production process. If we have a whole bunch of people and one machine, then a whole bunch of people are standing around and maybe one or two people are operating the machine. We add another machine that increases output by a lot, and then so on and so forth. But pretty soon we're adding so much capital to the production process per worker that we can't use those machines efficiently. And so it's going to be the case that we have smaller and smaller increases in output per worker. So what we want to do is take that observation about diminishing marginal returns and make some assumptions to try to, even though this is going to be really notation laden, try to cut it by as much as we can. So we're going to suppose that we have a closed economy and we have no government. And so we just have the private sector, consumers and households. We're going to suppose, because this is a good assumption, that savings is a constant fraction of income, and again, income per worker. So you could think about that fraction as being this little s. In equilibrium, we said, so this would be, where did we see this? Chapter 14 in the loanable funds market. That would be one place to think about this, that in equilibrium, we have the quantity of savings being equal to the quantity of investment. And then the final assumption that we're going to make is that depreciation is just a constant fraction of the amount of capital that we have in place, and again, per worker. So how do we think about this? Or what are the implications? So real GDP is just going to be consumption plus investment, because G and net exports are equal to 0. This is the amount of savings in the macroeconomy, and we're saying that it is equal to investment. In earlier equations, or earlier instances in which we talked about the evolution of the capital stock, we said the capital stock next period is the capital stock that we have in place this period, plus investment minus depreciation. And that's kind of what we're doing here, except that we're scaling by the labor supply. So capital per worker next period is equal to the capital per worker that we have in place this period, plus the amount of investment. So this is investment this period, minus depreciation. So we just have depreciation as a constant amount of the amount, a constant fraction of the amount of capital that's in place per worker. So these things together tell us some stuff. So I'm going to say it in words, and this is kind of like what's in the textbook. But then what I want to do is illustrate it. So if depreciation is increasing at a constant rate, but investment, we know that depreciation is increasing at a constant rate. We also know that investment is increasing at a diminishing rate, or at a decreasing rate, because investment is related to income per worker by this fraction S, and income per worker increases, as we just saw in the previous picture, at a decreasing rate as the capital stock. So in other words, in relation to what? As we increase capital per worker. And so our conclusion from that is that at some point then, depreciation is going to be equal to investment. And this is what we're going to call a steady state. And importantly, what we're going to see is that growth stops. So let's look at a picture. So on the horizontal axis, we have capital per worker, and on the vertical axis, we're going to be initially just measuring depreciation and investment. I have some numbers here because if it helps you, you can look optionally at a numerical example that I'm going to post on Canvas, but for right now, we're just going to not worry about those numbers. So, oops. See if we can correct this. Okay, so let's do this. Not that. We're going to look at this in terms of our picture. So I have lots of fancy pants stuff that we can do. So let's see. Okay, we can make it maybe that way. So what do we have? We have depreciation as this straight line because depreciation is a constant fraction of the amount of capital per worker that's in place. Investment is just a fraction of income per worker. And if you go back to, let's go here, if you look really small down there, you can see that we saw that diminishing marginal returns relationship. And so, what can we observe? We can observe that, for example, using this number 100, at a capital per worker level of 100, depreciation is 2 and investment is 3. So what does that mean? That means that capital per worker has to be rising because we're doing more investment, we're adding more to the capital stock than is being used up. And that's going to continue as long as we'll see, we're at a level of capital per worker less than that amount. Suppose we're over here where capital per worker is 400, so we've got a whole bunch of capital in place per worker. The depreciation is, say, 8, and investment is only 6. So in that particular case, we have more capital that's being used up each period than is being put into place, and as a result, we would expect that the capital stock per worker is going to decline. And so, as a result, what we can conclude is that there's got to be a point at which capital per worker is the level of capital per worker is such that investment and depreciation are exactly the same. And at that point, what we're going to observe is that we have what's known as a steady state. And at this steady state, we have kt plus 1, k over L in period, sorry, k over L in period t plus 1 is exactly equal to k over L, capital per worker, in period t, because investment is exactly equal to depreciation. So what can we do with that? Well, what we can do with that is now look at output per worker. So we've got the same picture here, which for whatever reason is working now in terms of my animations. So here is our steady state level of capital per worker, and we're going to superimpose upon that output per worker. So what we can observe here is that output per worker is defined and numerically in my problem is going to be 15. So in particular, what do we observe? In these periods, or in these, over this range where we're below the steady state, we have a situation in which there is an increase in capital per worker because investment is bigger than depreciation. That's what we saw in the previous slide. And as we move in this direction, right, so as we move this way towards the steady state, along this production function, we're moving up. But what can we conclude? We can conclude that as we transition, as we move to the steady state, output per worker or equivalently, again, it's really important to remember this correspondence, income per worker initially is growing quickly, but then growth slows, right? And that's the application of diminishing marginal returns. So as we start from no capital per worker to having 1 unit, 100 units, and so forth, all the way up to what I'm asserting here is this is my steady state number, we see growth in income per worker that initially rises quite sharply, and then as we get farther and farther and farther along, it tapers off. And we can then use that to motivate a phenomenon that's known as catch-up growth. So catch-up growth is sometimes also referred to as convergence. So the question is one really of optimism. Might we expect that eventually all the countries in the world will eventually be rich? Why might the answer to that be yes? Well, poorer countries can replicate the production methods and technologies and so forth of developed countries. And if poor just simply means that you're starting at a lower stock of capital per worker, of course, than in rich countries, then a given increase in the capital stock, again per worker, is going to cause much more rapid growth in a poor country than in a rich country. Why? Again, due to diminishing returns to capital, diminishing marginal productivity of capital. So in other words, we might posit that we could order countries along this line according to what their initial level of real GDP per capita is and their growth rate in their subsequent growth rate in real GDP per capita. And if you had a country that was down here, this would be a relatively poor country. And again, if poor just means that they don't have much capital per worker, physical capital, or as we'll surmise, or as we'll add in, human capital per worker, then as that gets added, they should have very, very high growth rates. Whereas if you have a relatively rich country that adds more capital per worker, its growth rate is going to be relatively slow. And this is the idea of catch up growth. So, what do we observe? If we look at countries that have currently high incomes, we see that there has been fairly significant catch up growth. Sorry. So, in particular, here we have real GDP per capita in 1960, and then we look at their subsequent roughly 40 years worth of growth from 1960 to, or yeah, 40-ish, 50 years of growth from 1960 to 2009. And in 1950, the United States and Switzerland and Luxembourg were relatively rich countries in terms of GDP per capita, and they had relatively slower growth rates in GDP per capita. Whereas you look at Japan and Ireland, but particularly Taiwan, South Korea, Singapore, Hong Kong were relatively poor economies in 1960, and they had among the highest of growth rates over this period from 1960 to 2009. So that really suggests great optimism about the prospects for alleviating poverty in the world. However, and there's always a however, we need to qualify this. So if we, instead of just looking at rich countries, we look at all countries for which statistics are available, we don't see the same kind of rosy picture. We see some countries that had low levels of gross domestic real GDP per capita in 1960 that continue to languish and in some instances experience over this time frame on average negative economic growth. We see, as we saw before in the previous picture, other countries that just have phenomenal growth over this time period in relation to where they started in 1960. China, South Korea, Japan, Taiwan, Singapore, Hong Kong, so forth, Malaysia. And then we see some other middle income countries that didn't grow very much. So they started off kind of middle of the road in terms of GDP per capita, and they remain not sort of superstars in terms of growth. And we already talked about Venezuela as a particularly sad example in the previous set of notes. So what can we conclude from that? This is where the role of institutions and incentives comes in, and it is going to allow us to also kind of think more deeply about what we're going to transition to. So we can see that many countries in the world haven't been catching up. These videos are kind of interesting. I'll link them in separately in Canvas if you wanted to look at them. But why is that? Well, it's because growth in GDP per capita is going to be driven by more than just the capital stock per worker. So let's look at this a little bit more. Let's consider what happens if we have an economy that decides to save more today. So the economy moves from a savings level of S0 to a savings level of S1. S1, of course, being a higher fraction than S0. So we see that this investment line shifts up. The production function itself isn't shifting up. It's just that we're choosing to save a higher fraction out of every level of income. Well, what does that mean? That means then that the economy is going to grow, but it's going to grow to just a point. So we see that the economy will move from its steady state level of capital per worker, say of 225, and output per worker of 15. And again, the numbers are irrelevant. It's just to have some numbers here that when the economy decides to save more, then we see this movement to a new steady state because the level of investment is going to be bigger than depreciation. So depreciation isn't changing. So the country's adding to the capital stock or is experiencing what's known as capital deepening, an increase in capital per worker. And we transition along this curve and along the depreciation line to the new steady state, where, of course, we also see a higher level of output per worker. So that's awesome. So what do we learn? We learned that if we increase savings, that's going to lead to a higher standard of living. And that initially we have pretty fast economic growth as a result of that saving, but that tapers. And eventually, when we get to here, if there's no change in the capital stock per worker, then there is no change in growth in gross domestic product. So importantly here, at a steady state, everything is steady. It is the case that there is no further growth in output per worker, which is important because that's our measure for income per worker and feeds into how we think about standards of living. There is no further growth in output per worker. So we experience, as a result of more saving, initially, temporarily, faster economic growth, but it tapers off and eventually we reach this steady state where we're just sit until there's some other change. So there are several predictions of the Solow model that are consistent with evidence. Countries are going to grow faster the farther their capital stock per worker is away from the steady state. That's the idea of catching up growth or convergence. Countries with higher savings rates have higher GDP per capita. So it's not that savings doesn't matter. In fact, it does matter for a country's standard of living, but it can't explain sustained long run economic growth. And indeed, for most economies, one prediction from the Solow model, as we've described it so far, is not consistent with the evidence. So again, the Solow model on the previous slide is telling us that once we get to that steady state, long run economic growth is exactly zero. But we don't see that. We see countries that continue to grow in the long run. So if we can have temporarily faster growth from increasing our savings or increasing capital per worker, what can explain sustained long run growth in our standards of living? Well, we have two things that we haven't considered. So we haven't considered human capital and we haven't considered technological knowledge or technological progress. So, what can we say about human capital? Well, we can say that human capital certainly correlates with higher levels of GDP, correlates positively with higher levels of GDP per capita. So, countries that have higher measures of human capital, say by looking at average years of schooling or literacy rates or other kinds of measures, are countries that also typically have higher GDP per capita. However, does that mean everybody needs to just cram more and more and more knowledge into their heads? Again, what we can see is, or what we can argue is that unfortunately, there's limits to growth from expanding the stock of human capital. Human capital, like physical capital, is subject to diminishing returns and it depreciates. So, diminishing returns. The phenomenal ability to acquire further knowledge from primary and pre-primary education that comes about just by basic literacy is huge. Secondary school, you learn, more skills, but we could argue that the marginal contribution of secondary education is smaller than the contribution that's coming from preschool and primary education. And similarly, college is great. Lots of things are great. It's going to be great after COVID, but you could argue that there are diminishing returns that are applying that would apply to the further acquisition of knowledge, and it depreciates. In the very extreme case, when you're dead, it's gone. But for most of us, we have a use it or lose it kind of feature in our brains as well. And so there is a depreciation in your knowledge and level of understanding. As I stand here as an old person, I can attest that. So human capital cannot explain sustained increases in long run economic growth. We would have the same prediction that we had from talking about higher savings rates. If we increase human capital per worker, that's going to be something that will give us temporarily faster growth, but diminishing returns will eventually set in. So that brings us to technological progress. So technological progress, again, we defined in the previous set of notes, is essentially the generation of new ideas. And I like to think about technological progress there as ideas, and you'll see that on the next picture. And how does that play out in the production function? In the production function, again, it's this A parameter. So we didn't do anything with that yet, but here we go. Let's suppose that we consider new ideas buffeting this economy. What happens? Well, initially, let me remind ourselves of where we are. We're going to start off here at this steady state level of capital per worker and output per worker of 15. And what we have is sitting out here in front, this A parameter that is representing technological progress. So what happens? Well, if we have better ideas, that shifts up the whole production function. It means that we're better able to take the resources that we have and combine them in ways that generate more output per worker. If we have this escalation of the production function, then that also means that for any given level of income, we have more investment. And so that investment then fosters capital deepening. And with that comes an escalation in output per worker. And so if you imagine this process continuing again and again and again and again, the generation of new ideas means that we get to, move up and then, over even farther to higher levels of gross domestic product. So in the textbook, they had this, sort of over and up and over and let's see, over and up kind of picture, and that's what they were getting at is that by having more and more ideas, it allows this whole production function to shift up, and we can see sustained growth in gross domestic product. So ideas can, in principle, generate unlimited growth. Ideas are can do that because they're freely shared and they don't depreciate with use. Just because I have an idea about how to do something doesn't mean that you can't use that same idea. And one person's ideas may promote another's, or a company's ideas and innovations may lead another company to build on that. Now, there is the downside of ideas in this issue that ideas don't depreciate with use. Sometimes it's difficult to prevent other people or companies from stealing an idea and using it to their benefit. So this problem of excludability, or specifically the non-excludability of ideas, that once an idea is out there in the universe, it can be freely appropriated by anybody to use in whatever manner they desire, sometimes can mean that there is too little investment in the generation of ideas. But that takes us right back to our earlier comments for economic growth, which is just that it's really important for government policies to promote innovation and foster stable institutions. And one way of promoting innovation is with property, by ensuring property rights, but also patent protection. So patents and copyrights, for instance. Patents and copyright legislation, things that protect intellectual property. So intellectual property protection. If we have an economy where we have institutions in place that foster this, then it is likely that that we'll be able to see this ongoing generation of growth. Sorry, I'm distracted. My dog is doing weird things. So what can we say then by way of conclusion? Well, we can remark that if we look at the broad arc of history, the absence of technological progress explains why growth took so long to occur. And in the textbook, the authors describe that, and the necessity of living hand to mouth really prevented resources from being allocated in any way that could have led to technological progress. Optimistically, technological progress can allow countries to break the cycle of poverty. So we see that with catch up growth, but then that can just be even more profoundly described with the promise of having a production function itself that's shifting up. And if there are no limits to technological progress, then optimistically, there can be no limits to growth. Now, I want to stress again that what I'm not saying is that we have growth with abandon, where we, destroy all of our resources and we don't have trees anymore and so forth. I'm not talking about growth in an environmentally unfriendly way. I'm saying we can have growth that happens in a sustainable way because of technological progress. Now, one way to get a handle on kind of how are we doing is with growth accounting. So again, I don't want to dwell too long on this, but what we are going to do is you take the production function, and we have as a general rule in calculus that the growth rate of a product is the sum of the growth rates of the individual terms. So if you don't remember that calculus, or you don't like it because then, or you've never seen it, don't worry about it. Just take it as faith that what we can do is we can take this production function and say what we have up here in levels, we can then say, well, all right, in growth rates, the growth rate of output per worker is going to approximately be the sum of the growth rate of technological progress, or excuse me, is going to be broadly defined technological progress plus this other piece that we're calling capital deepening. So the extent to which capital per worker is rising. So if we wanted in real life to try to get a handle on to what extent do we see technological progress happening, we can do it through this growth accounting measure because we know what Y is, we know what L is, we can estimate what that is, and we know what the size of the capital stock is. So we can deduce the level of technological progress by what's not explained. So in other words, this chart is from Brad DeLong's website. He is an economist out in Stanford. And what I have is this broken apart by various time periods. So when we have the growth rate of gross domestic product, we can look at that on a per worker basis. And we know the contribution of capital deepening. So we know this, and we know this, and we know this because we can measure these things. And we deduce this by saying these two things have to sum together. So as a practical matter, in real life, we get the 1.8% by taking the 3% growth, subtracting from that 1.2%, and deducing the annual growth rate of this technology parameter. And so what you can see is that through these calculations, we can observe this slowdown in technological progress that happens beginning in the 1970s and continuing through the mid-1990s, but then a return to growth that until the Great Recession, people were quite optimistic about, because it sort of suggested that this period of languishing productivity, languishing technological progress was going to be an aberration. It's an open question as to whether that's true. So by future growth, optimism or pessimism, what I'm asking about is really, can we see strong rates of growth in our standards of living? And if so, why? So Bob Gordon is a professor at Northwestern University. He wrote a book in 2017 that you'll see, you can hyperlink to here, and you'll see referenced on the summary PowerPoint notes as well. And his basic shtick is that economic growth as we know it is, of course, a fairly recent phenomenon in history, and you can think of it as having occurred in three waves. And the third wave was generally as a result of the innovation that is embodied in telecommunications and computers. And his research is suggestive of the fact that we may have by now exhausted the benefits of that third wave of innovations. There's a couple of kind of short YouTube videos on this that I'm going to link into Canvas that if you're interested in this debate, I would definitely encourage you to look at. They're really quite informative. There are lots of others who say, well, Professor Gordon, you're kind of a sourpuss about this because we're really on the cusp of a fourth wave. And the fourth wave is kind of pitched in two different ways. One is this notion of new and different ways of using technology embodied in computers and the internet to foster more and more growth. The strongest proponent of this that I have seen is Professor Bjorn Fossen, who is jointly at, I think, MIT and Stanford. And so you could go to his website. I'll again link this into Canvas if you're interested in it. And he's got a great TED Talk that I'll also link into Canvas. Others, and this links out to the Environmental Defense Fund, are optimistic about the prospect of growth that, again, is this fourth wave, not necessarily independent of these things, but fully independent, but its own kind of source of growth as we come up with innovations in energy usage and storage, as particularly in an effort to protect the environment. And so you can read about that as well if you're interested by referring to the stuff that I put on Canvas. So, wish I knew the answer. I tend to fall more into this camp than Professor Gordon, but his book is really, really an interesting read if you wanted to go down that. So we have a whole lot of mathy stuff in these notes, and what I want to do is suggest the key takeaways. So one key takeaway is that if we want to think about standards of living, we are going to look at GDP per capita, real GDP per capita. And our premise, as we saw before, is that this is related in a good way to well-being. We'll have a little bit more to say about this as part of the summary notes, related to well-being positively. So in the sense that we saw in the previous set of notes. Because there are limits to growth in standards of living coming about by adding more people to the labor force, we focus on labor productivity. And when we focus on labor productivity, the key thing that we saw as fostering sustained economic growth is technological progress. So the key ingredients to economic growth are, of course, having more human capital and physical capital per worker and technological progress. So maybe I will do this. This is per worker, of course. Labor is going to matter, but we have the murkiness that if we have more people, that might not be something that increases GDP per capita. So we need to just be careful about that. If we have more capital per worker, that's going to lead to growth, of course. But that growth is going to be temporary. And the key to sustained ongoing growth in the macroeconomy is technological progress. So technology or technological progress, which then brings us right back to thinking about the important role of institutions. So let me do this. That institutions are really, really important in terms of fostering economic growth because they are going to be the underpinnings for ensuring that technological progress continues. So with that, we have reached the end. of material for the semester, and what you'll see in the next set of notes is just really a summarization and some areas that you could go if you wanted further reading.